In astronomy, an imaginary and convenient celestial sphere is used to study celestial bodies. The observer is always at the center of this sphere, with stars projected onto the surface. The vertical line connects the zenith point directly overhead and the nadir point below. The mathematical horizon divides the sphere in half, defining the visible and invisible parts of the sky.
Welcome. Today, we're going to delve into one of the most foundational concepts in all of astronomy, the celestial sphere. Now, right away, let's be clear. This is not a real physical object. It's a brilliant imaginary globe, a powerful geometric tool that astronomers have used for centuries to create a map of the sky and to make sense of the movements of the stars.
So here's our plan. We're going to construct this model logically in 5 steps. First, we'll get a handle on the sphere concept itself. Then, we'll look at 2 completely different reference frames, one built around you, the observer, and another based on the Earth's rotation. After that, we'll see how these 2 systems intersect to define key reference points. And finally, we'll discuss why this abstract model is so incredibly useful in practice.
So what exactly is the celestial sphere? Well, I want you to imagine you're standing in an open field and you are at the exact center of a gigantic hollow globe. Every star, every planet, every distant galaxy, they're all projected like dots of light onto the inner surface of this globe. Now, here's the clever part. The actual size of this globe is irrelevant. Its radius is arbitrary. What matters isn't the true, staggering distance to these objects, but their angular position on the sky. This abstraction lets us take the chaos of a 3-dimensional universe and neatly map it onto a 2-dimensional surface.
To begin building our model, we start with the most fundamental reference point there is, you, the observer. This first system, what we call the observer's coordinate system, is a framework that is built entirely around your specific location on Earth. Everything is defined relative to your personal sense of up and down. Okay, let's visualize the first element. Picture a perfectly straight line that goes from a point infinitely far above your head, passes down through your body, through the very center of the sphere where you stand, and continues to a point infinitely far below your feet. This is the plumb line. It's your personal vertical axis, the absolute up and down reference for your specific spot on the globe.
Now, where this plumb line of yours pierces the inner surface of our imaginary celestial sphere, it defines 2 critical points. The point directly over your head is the zenith, and its exact opposite, the point directly beneath your feet, which of course you can't see, is the nadir. These 2 points, z and z prime, become the fundamental poles of your local reference frame.
Once we have the zenith and nadir, we can define a horizon. But listen carefully. This is not the horizon you see when you look outside. This is the mathematical horizon. It's an ideal, perfectly flat plane that slices right through the center of the sphere, exactly perpendicular to your plumb line. It forms what mathematicians call a great circle, and it cleanly divides the entire sky into 2 halves, the visible hemisphere above you and the invisible one below.
And this is an absolutely crucial distinction to make. The mathematical horizon is a perfect, geometric concept. The visible horizon is the messy, uneven line of trees, buildings, or mountains you actually see. For the precise calculations of astronomy, we must rely on the former, the ideal mathematical horizon.
Now, this local system gives us 2 important types of circles for taking measurements. First, imagine a circle drawn on the sphere parallel to the horizon, like a line of latitude. That's called an almucanter. Any star on that circle has the same altitude or height above the horizon. And how do we measure that altitude? We use a vertical circle. That's any great semicircle that runs from the zenith down through a star to the nadir. So, that's the local observer-based system. It's perfectly valid, but it's tied to you. If you move, the whole system moves with you. For a universal map of the sky, we need a different framework, one that's the same for everyone. So now we're going to ignore your personal vertical and align our model with something much, much bigger, the rotational axis of the Earth itself.
Okay, I want you to visualize a second axis now, appearing inside our sphere. This one isn't vertical relative to you, it's tilted. And its tilt is perfectly parallel to the Earth's own axis of rotation. This is the axis of the world. From our perspective here on Earth, the entire celestial sphere seems to pivot around this single axis once every 24 hours.
And just as the plumb line gave us the zenith and nadir, this new axis of the world gives us the celestial poles. These are the 2 points where this rotational axis intersects the sphere, the north celestial pole and the south celestial pole. For any of us in the northern hemisphere, the north celestial pole, or point P, happens to align almost perfectly with a certain famous star, Polaris. Following the same logic as before, we can now define a new great circle. The plane of the celestial equator is perpendicular to the axis of the world. You can think of it as simply taking Earth's own equator and projecting it outwards onto the celestial sphere. This great circle divides the entire sky into the northern and southern celestial hemispheres.
Now, in this rotational system, the apparent daily path of any star traces a circle on the sky. This path is called a diurnal parallel, and it runs parallel to the celestial equator. And to measure a star's position in this system, we use circles of declination. These are great semicircles that run from the north celestial pole through the star down to the south celestial pole.
All right, we have now constructed two completely independent systems. One is based on you, the observer, with your zenith and horizon. The other is based on the Earth's rotation with its celestial poles and equator. The most important, most useful points on our celestial map are found where these two systems intersect and overlap.
The crucial element that connects these two systems is the celestial meridian. This is a unique great circle. It's special because it's defined by the four most important points we've established so far: your zenith, your nadir, the north celestial pole, and the south celestial pole. It's the one circle that contains the key points from both systems, and it slices the sky perfectly into an eastern and a western hemisphere.
And it's the intersections of these fundamental circles that finally give us our familiar cardinal points. You see, where the celestial equator crosses your mathematical horizon, we find the exact points of east and west. Where our newly defined celestial meridian crosses the horizon, we find the points of north and south. And finally, where that same meridian crosses the celestial equator, we define the upper and lower equator points.
This table provides a concise summary of all these fundamental points we've just constructed. You can see the poles from the observer system, the zenith and nadir. Then you have the poles from the rotational system, the celestial poles. And finally, you see all the cardinal points that are created where our main circles, the meridian, the horizon, and the equator, all intersect. So, after meticulously constructing this rather intricate geometric model, piece by piece, we arrive at the most practical question of all. What is the purpose of this complex system? Why do we need it? I mean, why go through all this trouble defining these imaginary points and lines and circles? Well, the answer is that the celestial sphere is an incredibly powerful tool for prediction, for measurement, and for description. Really, its main purpose is to create order. It gives us a consistent grid for the entire sky, very much like longitude and latitude on Earth, which lets us precisely map the positions of objects. Once we have that map, we can track and predict their apparent movements. Ultimately, the celestial sphere provides the universal framework that is required for nearly all fundamental astronomical measurements.
And so, we can conclude with this final thought. The celestial sphere is a perfect model of what we see from our vantage point, a sky that appears to rotate around a stationary Earth. For mapping and predicting what we see, it works flawlessly, but its very construction is based on an apparent motion. The great leap forward in science was realizing that this elegant model, as useful as it is, actually masks the deeper physical reality, the complex, true motion of our own planet as it spins and orbits through space.
Thank you, friends. Strive for understanding and become wiser. See you soon.